I guess we can start. So thanks for coming. I'm Matija. I'm coming from a company called SmartCat. We recently started working, and we're working on big data technologies, and we're fascinated by data. So you can find us at smartcat.io. And today I'll be talking about breaking free from relational databases. And today's agenda is talking about what's actually wrong with the relational database as we know it, what are actually our needs today, and why we're moving to different technologies. I'll talk a bit about Cassandra and about its architecture and why we're using it today. I'll talk about use cases and some benefits we gained, and also I'll go through some of the things in our learning process which hurt us the most, and some common mistakes that people I see make a lot. And the last thing I'll talk about is a couple of migrations we did. We did migrations from MySQL and MongoDB and our experiences. So what's actually wrong with a relational database? You can say that we understand it. We worked with it for a long time. It's reliable. It does what it's supposed to do. It's been around for ages. That's one of the important things, because when you work with a certain technology for a certain amount of time, you begin to develop tools for both development and administration, and that makes life for us developers easier. And also, it's easier to maintain. If you have any problems, you can always ask on Stack Overflow, and you'll get an answer. And also, why do we need to change now? Because it worked great for decades. And one of the things we need to change it is because it's wrong by the design. It has design flows, and the architecture is wrong by today's needs. You cannot scale it. That's the problem. To make it work faster and make it be able to store more data, you need more expensive hardware. So only way you can scale it is scaling up. It has a really limited fault tolerance. It means that if you have any problems with the database, it's probably going to be on your instance, and you're really in a problem. There's some scaling models. I'll talk about one, but it's still not true scaling because of the design. And the problem we're solving the most is because it cannot handle huge amounts of data. And this is something that is not a problem we had 10 or 15 years ago. It's something that we are having right now. So this is one of the principles of scaling the relational database. You have a single master, which is doing all the writes. There are a couple of ways you can translate those writes to the slaves. Usually we're using transactional replication. And these slaves are usually used for reading the data. So you have a single point of write, which is master, and it makes sure that there's an ACID compliance. And then you have as many slaves as you need. You can put them in different places of the world where this data is being read. But what's the problem with this approach? The problem is that today networks are not reliable. That's something we have to live with. And if you think that a network is really fast, it's reliable, the transportation costs are zero, you're really wrong. Because things like this can happen. It means that there can be a network split. There can be maybe Amazon rebooting the whole region. You can have a hardware failure. If you're hosting the database inside your data center, you can have hardware failure on a switch. You can have a hardware failure on machine. And also there's a latency. The latency is one of the biggest enemies when you're developing a distributed system. So in this case, we have a network split, which renders this master unavailable. Sorry. It means that if you have a recovery mechanisms, which are for most databases, relational databases are manual or semi-manual, then you have a mechanism which will make one of these slaves a master. It will save your day. Your application will continue to serve. You'll continue doing writes. But there's another problem. What happens when this network gets fixed? Then you have another instance which still thinks that it's a master. Then you have some data is being written from this master, and then the master that was previously a master, the top one, is not in a consistent state, and then you have a problem. So what are our needs today? Why we need to change from relational database to something else? That's the main question. Why is the technology that was great for the last 30 years not sufficient today? That's the main question. Well, the problem is that 90% of the world's data, so all the data we have, is being generated in the past 2 years. And this number is just getting bigger and bigger each day. And one of the most important things is that, excuse me, this data actually impacts your business. There's a lot of companies that do all kinds of analytics on their data, even machine learning. And all those things can impact your business. You can get some answers which can help you make changes and make your business better. But also, there are systems that can learn and adopt. And of course, personalized experience. Anybody who ever shopped at eBay or Amazon or any other store, watched movies on Netflix, it's getting more personal and personal. Each time you hit the click, one of your friends buys something. And this is one of the most important aspects of marketing today. And of course, us as humans, we have problems with hurting everything. We're storing everything we have. So we need more technology to help us store everything we have. I mean, there's probably a lot of you guys that have basements or any other storages that you never touched in a couple of years, but you need those stuff. So the 4 things we need today is actually availability. Our application needs to work all the time. If your application has a downtime of even a minute, if somebody comes to your application and doesn't work, he'll probably never come again. The second thing is scalability. This is one of the problems of the relational databases and a typical monolithic systems is that it usually can scale really good up. That means buying better hardware and a bigger box. But the problem is scaling it horizontally. Especially if you have an application that works in different regions, in different zones, and you want to offer all your clients local experience, so experience of accessing a local service, you need to deploy it on all kinds of regions if you're deploying on AWS or Azure or whatever system. So you need this horizontal scalability also for giving your system more resources, because it's easier to buy 10 instances of quad-core machine with 16 gigs of RAM instead of buying one instance of all that crammed into one case. Also, one of the important things of distributed systems, also one of the biggest headaches of distributed systems is being fault tolerant. There are also some interesting topics we can talk about is how the distributed systems are actually made to fail, because with this approach you're never going to get downtime. Also performance, as I said, some users, they visit your application or website and they see that it's not giving them response. There's a study that if your tab doesn't load in 2 or 3 seconds, you're probably going to switch to another tab, so you probably lost another customer. There are 2 main concepts which the relational databases and NoSQL databases are based on. So these are properties of these systems. First one, the one we're used to using and the one which is more natural to us is an asset compliance. It means that the writes are atomic and consistent. The transaction is isolated and durable, making sure that if it's written to disk, it's actually written to the disk. You can read it right away. There's a lot of documentation on this, so please, if you want to go check on web. And also the second one is base, which means that the basically available solid state and dimensional consistency are properties of a NoSQL and most of the distributed systems today. Basically available means that we are making the system available no matter what problem we have. If we have one of the parts of the system down. Soft state means that when we write something into the system, it's not going to be consistent in all of its parts right away, but we're having a state which will change through time. And at the end of that time period, we're going to have a consistent state throughout the system. And of course, eventual consistency. This is one of the most critical points and properties of a distributed system, also distributed database, and the one which will probably cause you most headaches if you start developing with a distributed database, because we're used to doing reads, writes, and writes, reads, but this cannot be done, especially in Cassandra, which we'll come to later. So Cassandra is a database which is completely, totally scalable and distributed. It's a row partition stored, meaning that all the data is being written into partitions. So we'll get to the physical data model later. It's really fast, scalable, and fault tolerant. It means that it's totally distributed. There's no single points of failure. There's no master-slave architecture. It's a share-nothing architecture, which means that if any part of the system fails, you will probably not even notice. You'll probably get an email with a log that one part of the system has failed. Also, active everywhere design. This is one of the really interesting things about Cassandra. If you remember the previous model about scaling the relational database, you had a master which does writes. So you have a single point of failure, but you also have a single point of access. And then you can access slaves for reads using some of the routing software or any other way you want to use it. But this is different. I'll show you in the slides. And there's also a native multi-data center support. This is really important thing because, as I already said, if you want to provide your applications in different parts of the world, you're probably going to have data centers which are closer to the users. And this will make your application feel like local. And this is important. So this is how the Cassandra architecture looks like. It's a share-nothing architecture. You have nodes which form clusters. Nodes communicate between each other. And the important thing is that you can access any of these nodes. And you will, I'm saying eventually, but you will get the data you're looking for. So it looks like this. You have a client. There's drivers for most popular languages, so it's easy to start the implementation. Documentation is pretty good. So you have a client which is trying to contact any part of the database, and it can be done. Usually the client's implementation is so that it's going through round robin. There's also some load balancing policies, but I won't get into too many technical details. But sorry, what's important is that for each request, there can be a different coordinator. So if you contact a database, you know the topology of database, so the driver is pretty smart. It can contact one of the nodes in the cluster. This node will look where the data you're searching for is. And then the first node that returns a response, this response will be transferred to the client, and you'll get your data back. There's a lot of stuff going on under the hood. The nodes are communicating between each other using gossip protocol. There's a lot of technical stuff, and I won't get into that. So if you're interested, you can contact me. We can talk about it. You can look it up on the web, but it's really interesting technology. Also, I said that there's a native multi-data center support. This means that you can have a cluster in Europe, and you can have maybe a cluster in Asia. These clusters are aware of each other, and they communicate, they share data, their data is being replicated between clusters. And this is one of the biggest benefits when switching to architecture like this. So it means that if a read or write request comes at one node, it will first do it will execute the statement, or if it's a read or write locally, and then it will transfer that to another data center. And this is all happening automatically. You don't have to do anything. So that's one of the powers of this database. So what's the data layout? I already said it's a partitioned row storage. There's two types of rows. There's a slim row. It's basically an entity per row. You have key values for the entity properties, which are the name and value, and they represent a cell. And basically, this row is as wide as many properties you have in an entity. The other approach are wide rows. Wide rows are interesting because you can have more data in a single row. Reading that same data is being read from a single row, especially if you're using the old hard drives, that's a single disk sake. This data model is really important. This physical data model is important because this will actually help you make data models or break your application, because there are a lot of limitations, because you can think about this as a map of maps, and you know how these maps can be searched. So having all that in mind, we're solving some of the problems, but we're still inheriting some of the problems from concepts of the distributed data systems. What are the Cassandra's use cases? Try not to fit everything into Cassandra. That's the first advice you can have. And what are the perfect use cases? Those are the IoT applications where you have some time series data, some measurements, maybe even product catalogs or in the retail applications. Of course, activity tracking, user tracking, fraud detection. There's a lot of use cases that Cassandra really excels in. But also the benefits of this architecture, because the architecture is solving some problems. We have a reliable storage. That means that if you get a response from a database that the data has been saved, you can rest assured that the data has been saved. It's reliable also in the means of fault tolerance. The performance is really linearly scalable. As many nodes you add, that many performance more you're going to gain, and it's really like that. It's not a marketing trick. Easily scaling on commodity hardware. I already said that relational databases have problems regarding the scaling up the architecture. Here you can have nodes on whatever machines you need and just add them into the cluster. And also the problems that we had regarding the relational databases in some use cases, of course, these are solved by design in Cassandra. But also there's a question at what cost? Okay, we solved some problems, but there must be some bad sides to this, because you cannot have everything done perfectly. You have to have some drawbacks. So the question is, how did we get into working with Cassandra, and what was our learning process? So first of all, the first thing that you see when you start working with Cassandra is the SQL syntax. That's the syntax of writing the data model, writing some queries in a client. It's a SQL SH client. So it's basically a command line tool. And when you look at it, the syntax is really familiar. It looks like SQL, right? But this is not true. The problem is that syntax looks familiar, but when you see something familiar, you're probably going to do it the way you already did, and that's the problem. You're going to get into problems because the data modeling is completely physical data modeling, and logical data modeling is completely different than your relational databases that you're used to. Of course, the next thing is when you have an application and you already have some database under it, and you want to migrate to Cassandra or any other distributed database that uses this data model, you're probably going to have copying over the data model, and you're going to think that everything's going to work because SQL is already familiar. And this is also a problem, because the way the data is being stored in Cassandra dictates the way that we design our data models. And these data models are actually optimized for reads. And the problem is that you cannot easily extend the data model and support additional queries. But you have to add another data model which will support your query. So data duplication is there. That's one of the drawbacks. But I don't think it's a drawback, because the database itself solves all these problems. So one of the problems we also had, of course, because the relational databases comply to the ACID properties, you're used to doing some writes then reads, because if you have an entity in the database, you write certain property to it, you change property, and then you read it again to return it to a client or do something else. And this is a problem, because you have a client, as I already mentioned, which can contact any of the nodes. And also, nodes replicate data between them in eventual consistency. So you have a problem that you write something, and then when you try to read it, if you're reading from another node, which wasn't updated, you're having a problem because the data that you just written is not there. That's the problem with eventual consistency, and trust me, we had a lot of these problems. So it's something that you have to understand. Eventual consistency is concept, and you have to understand it to be successful. So also one of the problems we had is read-write. It's not that big of a problem as write-read is. Write-read, it starts with wrong. So read-write is another anti-pattern. We're used to it because we get a certain pieces of data, we write it into the database, then we read it again. Sorry, we read the data before we write it in again. So we have a mutable object, which is being read from the database, some properties changed, then written to the database again. This problem is also one of the problems in the distributed data systems, because when you read the data before you write it in again, there's probably some other changes to the same data which you will not pick up, and then you will have the stale data in your database. So you will not have the latest data in the database, and this is wrong. Trust me, we did this more than once, and we really had problems with it. So we had a project with Mongo, and we wanted to migrate from Mongo to Cassandra. And of course, MongoDB is easy to use. You have document store. You can put indexes on it. You can support any type of query really easy. And so we written data models in Cassandra, and we saw that we are missing some of the queries, and we just slapped secondary indexes on, and it's fine, it works. But the problem is with secondary indexes that these have to be distributed also, and then when you're reading something that's affected by the secondary index, then you have to read from all the nodes. It's really a big performance issue. I presume that it's there because there are some corner cases which you have to solve with the secondary index, but the rule is don't use them. So migrating from relational database is, first thing is that you need to understand how your data is being queried. Because data model in Cassandra is query-based, and all the data written in the database itself is optimized for reading. So you need to understand how your data is being queried. If you have an R&D project and you're probably developing constantly changing the way you're accessing your data or writing your data, and you're constantly changing your requirements, I can't say that Cassandra is perfect for this, but there's when you're migrating from a project that is already there, okay, you can make changes to the data model along the way, but the problem is that you need to understand your queries. The second thing is that conceptual model, if you did your data modeling properly, the conceptual model is reusable. And of course, there are certain ways which you can integrate Cassandra into your system, but also keep the data in any previous relational database until you're sure that Cassandra is working and your data is there, you can get it back, and there's no problems. Of course, this is one of the important things if you have a team which never worked with this technology. You can leverage the power of message queues and then store data in both databases, then at some point start reading from Cassandra until you cut this database out. Or if you're just separating data flows, this is one of the legit ways because there are some data models which can stay in the relational database which are not fit for Cassandra, but you're also having some events or time series data which you want to use in Cassandra. So this is a good way to run them in parallel. And also, this is one of the most important things when you start development, especially on Cassandra or any other distributed system. Try to start it on 3 nodes, because if you start working with 1 node, you won't have any of these problems I already talked about. Everything will work, and then when you deploy it on any deployment platform, you'll start getting problems. You'll start getting some weird things, weird errors. You'll have to go through logs and figure this stuff out. So this is the best advice I can give you for starting the development. Start with 3 nodes. There's a lot of ways you can do this. You can have Docker images. You can use Vagrant or whatever. There's even CCM, that's Cassandra tool for starting the Cassandra on localhost, a couple of instances. It's awesome. And one of the most important things is if you move to a distributed database or any other distributed system, try to leverage the possibility of parallel execution. So if you have bits and pieces of data on different nodes, you can actually leverage parallel execution, query all that data simultaneously in parallel, and get it all back at the same time, which will cut down your query times a lot. And of course, you cannot beat laws of physics. Don't expect to bring 1 gigabyte or 1 terabyte of data from your database in a couple of seconds, because it just don't work like that. So I always get back to this, how we migrated from Mongo to Cassandra. So MongoDB uses some kind of a relational model. We know that it's a document storage, but there's also relations between the entities. I already said that Cassandra is a problem, especially if you're new to it. You cannot use it effectively in research and development phases. Mongo is a great database for doing some research and development, especially if your API is changing, if your database model is changing, because you can slap whatever in it and it will work. And also, don't measure the performance. This is one of the problems we had we tried measuring performance between a Cassandra node and a MongoDB node. MongoDB works from memory. Cassandra works a different way. You can use memory caching in Cassandra, but it's not meant to work like that. Always use clusters. Mongo clustering sucks, so don't try that. And also, don't use secondary indexes. Secondary indexes are natural in MongoDB because it caches a lot. It uses a memory. It uses memory for that. Don't use that in Cassandra. And my advice would be, don't use MongoDB. So we talked about how Cassandra is great, how distributed systems are actually great, but there are a couple of things when you don't want to use Cassandra. First of them, don't use Cassandra when you don't need a scalability. So don't use a hammer to kill a mosquito. That's normal problem. But I see a lot of people and a lot of teams trying to move to new technologies just so they're, I don't know, working with new technologies, but they're actually putting themselves in a problem because they're trying to solve something with a technology which is not fit for the problem. Of course, if you have a relational model, this sentence is not complete, because if you have a lot of updates, it's not a problem. But if you have a lot of updates in a complex relational model and you need to update a lot of different entities in the database, Cassandra is not suited for this. Cassandra is basically awesome when it comes to log append, when it comes to adding more data constantly. But the problem is when you have relations and you cover some of these relations with a denormalized data model, you have a problem with updates. Of course, don't use Cassandra when you need a query flexibility. So like in standard relational database, you would create an entry. This entry is entity, sorry. This entity has some properties. And down the road, you can query this entity by any of these properties, and it works, and it's awesome. But in Cassandra, this is a problem. You cannot have flexible queries because your queries need to be supported by the data model itself. And of course, don't use Cassandra when you don't know what you need. This is the biggest problem we see all the time. So what would be the conclusion? So in Cassandra, the data model is query-based. This is a problem to a lot of people, but you need to understand the way the data is being stored on disk in order to read it back. You need to understand the physical data layout, which is actual how this data is being stored. And you have to respect eventual consistency. This is something that if you try to go against it, you'll fail. We tried, trust me, we failed. So it's just a matter of learning it and getting familiar with eventual consistency. Of course, I'll have to say that in Cassandra, eventual consistency is a wrong term, because in Cassandra you can have tunable consistency, which means that each query you can define a consistency. You can define totally consistent, but you're losing partition tolerance. But you can define a loose consistency, which is like eventual consistency, and you have all the bells and whistles that the database has. And of course, when you try to do this, have fun, because it is a fun technology, and there's a pretty interesting learning process. Thanks.